my name is Joe Chen, one of Simon Bauer's graduate students. Before Professor Bauer gives a talk, I want to just say a few words. First, we'd like to thank Professor Bauer and his family to make an effort to come here. Secondly, we'd like to thank the chairman of chemistry, Chemical by Professor Baird, and Earl Peters and Joyce. So it's really a nice occasion to have Dr. Bauer here. Everyone have heard many of his talks, his seminar, and lectures. This time, I hope he'll give a different view of what he has experienced in the past. So I think I'm just introduce Professor Bauer, so he's going to give a nice speech.
Should I come up there now?
Yes.
I'm overwhelmed. Dear colleagues and good friends, I lost count of the many ways there are for expressing my appreciation for your participation in this double birthday celebration. Please note the following dates. On March 7th, 1911, Ernest Rutherford, at a conference in Manchester, England, described his nuclear model for atomic structure. A month later, on April 8, 1911, Camerleonis across the English Channel discovered superconductivity of solid mercury. On October 12, 1911, I was born in Kaunas, Lithuania. Now, there's absolutely no relation between those dates, none whatever. However, what happened in March 7 and April 8 in 1911 left an indelible impact on the scientific landscape. And later October event proved to be of no consequences whatever. But there is another connection. Exactly 16 years plus 1 day, on 1927, October 13, Ben Widom was born in Newark, New Jersey. Now that was a significant event. Sometimes during the late 1940s, Ben and I met for the first time in Baker Chemical Laboratory. For reasons that remain unclear to me, he proposed that I direct his Ph.D. program in theoretical physical chemistry. I suggested that he undertake a quantum mechanics analysis of the dynamics of interaction between carbon dioxide and water. Several decades earlier, Eucken in Germany observed, via sound dispersion measurements, that the vibrational relaxation time of CO2 was greatly reduced by low levels of admixed H2O. His data showed an unexpected temperature dependence. In due time, Ben completed his analysis of the interaction between these two simple gases and accounted for Euler's temperature curve. His PhD dissertation was published in 1953. And thereafter, Ben shifted his research institute to statistical mechanics and joined O.K. Rice as a postdoc at University of North Carolina. After completing his appointment to North Carolina, our department was most fortunate in capturing him for Cornell. Ben's outstanding analyses of the structure of liquids, particularly of their phase behavior in the vicinity of triple points, and of much, much more, brought him well-deserved international co-op recognition. Concurrently, his reputation as an excellent teacher and his enlightening lecture has yet to be surpassed. In the meantime, in my laboratory, we developed a variety of experiments for measuring the interaction between CO2 and H2O. Marilyn Jaycock set up a photoacoustic experiment, and several graduate students measured CO2 relaxation times at high temperatures in shock tubes. Later, in 1984, the structure of the transient binary complex was determined in Harvard by Peterson and Klemperer. And much later, during 2004, Professor Charles Wilcox completed an extended calculation of the electronic energy surfaces for water H2O adducts for intermolecular separations from 2 to 8 angstroms for a wide range of angles of approach. There are indications that collisions with the second water molecule plays a crucial role in the kinetics of dissociation of the CO2-H2O complex. So, what's so special about this casual flirting between these two simple molecules? Well, recall that speculations regarding the existence of carbonic acid date back a century or more. However, we now appreciate their significant role, for not only as greenhouse gases, but also in photosynthesis, in physiology, geology, atmospherics, planetary evolution, and so on. In recent reports, CO2 and water have been detected in the atmospheres of exoplanets. That pair of simple gaseous molecules comprise the vapor of every breath that you inhale or exhale. So you're really well acquainted with it. Well, that makes it very personal. Now, how did I get to Cornell in the Department of Chemistry? Literally, in 1939, I escaped from Penn State. Backtrack to summer of 1937. My postdoctoral appointment at Caltech expired. I returned home to Chicago, and I walked through the halls of Jones Chemical Laboratory and wandered into the office of Professor Schlesinger, who was directing the department after Professor Stiglitz retired. He did welcome me, but in the same breath assured me that there were no vacancies that he knew of any USA Department of Chemistry. Well, several days later, he told me that at the School of Mineral Industries in Penn State, there was a vacancy for someone who will undertake to measure the swelling of sequences of various grades of coal upon coking. I thought X-ray diffraction would be just the right tool. Well, that was not the case. I spent 2 years measuring levels of expansion for various types of coal by mechanical devices I attached to a small coking oven that I constructed. I had to escape. So our sojourn in Ithaca from 1939 to 2005 is the story of our lives. In September 1939, Mitzi and I and our 3-month-old son arrived in Ithaca and rented a still incomplete small house on Maple Avenue. The department chairman, Professor Jacob Papish, soon became a friend and a supporter. At that time, several professors in the department were engaged in pioneering research for utilizing physical methods for chemical analyses. Professor Chameau and George Mason were exploiting microscopy. Professor Papish was looking for ecocesium by testing an extended collection of ores that he accumulated from all corners of the Earth, using a wide range of optical and X-ray spectrometry. And Professor Nichols measured metal ion concentrations via colorimetry. Professor Laubengehr was studying compounds of germanium, and Professor Johnson directed his efforts to to organic compounds. Lynn Hort had begun his extensive crystal structure studies, and Bill Miller started his syntheses of a program for fluorocarbons. Jack Kirkwood was the one and only theoretician. When I told Professor Papers that I wanted to construct an electron diffraction apparatus, he placed the department machine shop at my disposal. Harry Bush was a super mechanic and most cooperative. And over time, my family became a Cornell film team. Our two younger children were born in the old Ithaca Hospital. They attended the local high school. The two older ones earned their BAs from Cornell, as did David, Debbie's husband, and David's brother, Jack. Our grandson, Hayden, returned to Cornell to earn an MBA from the Johnson School of Business. His wife was graduated with a master's degree from the School of Industrial Labor Relations at Cornell. And during 66 years of our residence in Ithaca, Mitzi and I traveled on many excursions, mostly associated with science conferences. We explored countries both to the east, in Europe and Israel, and to the west, New Zealand, Australia, China, and Japan. But we never really left Cornell. For many decades, collaborations with students, and particularly with friendly faculty members in chemistry, aeroengineering, physics, chemical engineering, greatly extended my horizon in science. The Cornell that we left in January 2005 is a grand amplified version of the university that fortunately I was invited to join in 1939. I found in Google, and I recommend our younger friends who have not yet done so, some interesting facts about the current Cornell. Are you aware that there are more than 4,000 courses offered? There are 70 undergraduate majors in nearly 100 academic departments, attended by 14,000 undergraduates. Cornell is now twice the size that it was when I joined the chemistry department in 1939. Most significantly, there are over 7,000 postgraduate students on the Ithaca campus, nearly 900 in the medical school and 35 in Otar in the east. My research program in 1940 started at the machine shop, supplemented with a variety of items scavenged from many sources. At that time, very limited funds were available for the purchase of laboratory equipment. Most had to be constructed locally. Contrast the multitude of precision mechanical devices, electronics, well-engineered apparatus, and vacuum system components that one can purchase today. Extensive use of computers, sophisticated electronics, shock tubes, lasers, synchrotron radiation, spectroscopy over extended frequency ranges, and ongoing technological evolution began during my lifetime. I operated on the fringe of those exciting discoveries. I wanted to participate in all of them. And looking back, I should have developed a much sharper focus. Well, during the last 2 decades, I failed to maintain contact with current developments. All branches of chemistry have expanded beyond my scientific reach. I am pleased to acknowledge collaboration with many prominent scientists. I was fortunate to have rubbed elbows with a number of eminent contributors to our discipline. I felt humbled when some time ago I assembled a list of joint publications. At this time, I specifically mentioned Ed Dressler's initial development of the single-pulse shock tube, which proved to be a panacea for high-temperature gas phase kinetics, and my extended collaboration with Charles Wilcox. It seems such a long time ago when we first generated laser radiation via energetic chemical reactions and subsequently used lasers to monitor selected chemical conversions and measure their rates. Well, There was also a practical sideline. I studied via synchrotron radiation the structure of molybdenum cobalt catalysts used for refining gasoline. Well, I take the liberty to read a poem I composed many decades ago, which I read in my previous birthday celebrations. My window has tainted panes. My scenes through it I saw. The contorted walls of Norway's fjords, Milford Sound, the moonscape plain of Mitzpah Ramon, and the great Buddha at Kamakura. Pictures at the Hermitage, forests drenched in rain. Satellites in Guillen's caves, scenes on postcards, these remain. Another batch, but closer to my heart, of lecture rooms and laboratories, of multicolored spectra, of plasmas and microwaves, fleeting structures in picosecond time, of normal modes and relaxation paths, of symmetries and shock waves, libraries of words that pictures paint. The tint of my pain, pink or blue, is colored by my friends and those I knew. But of all the glow that pink implies, nowhere did I find the emanations that flow on the campus of Cornell. There my spirit dwells. However else would I have rather spent 6 decades plus, spring, summers, fall, and winter snow. And above all, I salute and thank all my forward graduate students, postdoc associates, and I thank you all for being here on this occasion to participate in this double birthday celebration. Thank you.
You're great.
Let me.
Society of Mass Spectrometry. Fred had a connection, Mike Cook, who was the editor of that journal. They said that they would be super delighted to have this paper by Simon. So he wrote this paper, went back, as he always does, doesn't just start at in 1930, he went back essentially to prehistory, talked about the discovery of isotopes, which of course are central to one's understanding of mass spectra, and then showed us what he had constructed for his Ph.D. thesis. So this was the instrument that Simon constructed, and as he explained, it was in collaboration with the machinists at the University of Chicago, but otherwise hand-built, including wiring the magnets by hand. Isn't that right, Simon? And it was a terrific job. And Fred also convinced Simon that it would be useful if part of his history of mass spectrometry, he showed an example of one of the spectra that he actually took with that instrument. And there it is. This is the spectrum of methyl chloride. I see in this an off-scale peak at molecular weight 15. That's the methyl fragment. I see a peak at 35. That's the chlorine. I even see a subsidiary peak at 37, which is the next isotope of chlorine. This is fantastic resolution for an instrument that was hand built in the 1930s, and the sum of 15 and 35 is 50, and there is the off-scale peak at 50, which was the undissociated methyl chloride. And Simon didn't stop with taking this great spectrum, but he also analyzed the electronic structure of all the fragments that were produced in this mass spectrum using the then new molecular orbital theory that was developed by Mulliken at the University of Chicago. I have that story right, Simon? Say yes. So following that, Simon, as he explained, had a postdoctoral stay at Caltech. And there at Caltech, he worked with R.M. Badger and with Linus Pauling. And in particular, with Badger, he wrote this paper, which has since become a very famous paper on the spectroscopic studies of the hydrogen bond, and in particular, relating the OH stretching frequency of a hydrogen bonded molecule to the strength of the hydrogen bond that's formed, and that relation between the shift in the OH frequency and the strength of the hydrogen bond is now referred to and has ever been since referred to as the Badger-Bauer rules, and that this paper is a historic paper that's been cited many hundreds of times and continues to be cited to the present day. Now, not many people have written a paper that continues to be cited 3/4 of a century later, but Simon was one of the few who did. Then Simon explained that he had a two-year stay at Penn State University, and in addition to analyzing coal, he also had this great idea of finding a density of states from a partition function. That means, in effect, finding a density of states from the thermodynamic properties of the molecule. He saw that he recognized that the partition function is essentially the Laplace transform of the density of states, and so saw that if you measured heat capacity over sufficient range of temperature and with sufficient precision, that one could then, in principle, invert that Laplace transform and get out the density of states. Many years later, others had the same idea, but Simon was the pioneer. He was 10 or sometimes 20 years ahead of those who had the same idea subsequently. That was a wonderful achievement. This is the instrument that, or one of the early instruments that Simon described when he said that after he came to Cornell, so this is now in after 1939, he wanted to build an electron diffraction apparatus. He had become interested in the structures of molecules long before that, of course, from his Ph.D. work and also from his postdoctoral work in Caltech. And so, again, in collaboration with the machinists, and in particular with Harry Bush, whom Simon mentioned in his talk, he constructed this electron diffraction apparatus. I got this figure from a paper that dates from 1950, with a paper with Julius Hastings, but it's the same apparatus or similar to apparatus that is used in many such studies. And I want to say something in particular about one of the things that came out of this study. This is these are the electron diffraction intensities that we found. In the particular case of chlorine substituted neopentane. The top two refer to the neopentane, the bottom two to the silicon analog, where the central carbon atom of the chlorinated neopentane is replaced by a silicon. I had joined Sci in the late 40s and early 50s, as Simon explained, and I was his first and last theory student. But I was interested also in the experiments that his other students were doing. And one day, I walked into his laboratory. I've told this story before. Some of you may remember it. I walked into his laboratory and I saw Simon holding up a photographic film, holding it up to the light. He would look at it for a while and then make a mark on a piece of paper. Then he'd hold up the film again, look at it again, make another mark on a piece of paper, and so on. And this continued. What he was doing was tracing out one of these electron diffraction patterns, tracing it out where it was showing essentially the spatial distribution of the density of electrons in the molecule as and the Fourier transform of the spatial distribution of the electron density. And so he was tracing that out by eye. This first one is one that he traced out by eye. The second was the same photograph as analyzed by a microphotometer. And here are the same things for the silicon. This is what he traced out by eye. This was the microphotometer tracing. Some people would have done the microphotometer tracing in order to check the correctness of what they saw by eye. In Simon's case, he was checking by eye to make sure that the microphotometer. So that was another wonderful story. Simon was very interested. This is again, I'm picking out only the things that happened to strike me most at the time that I was looking back on Simon's career. But he has studied a very large number of chemical reactions in which there's a significant deviation from what is otherwise one of the standard theories of chemical reaction kinetics, the RRKM theory. Rice, Ramsberger, Hassel, Marcus. And in this case, he was studying the inversion of the inversion at the nitrogen center of the aziridine molecule. So the inversion at the nitrogen center is much like the inversion that occurs in ammonia. But in the case of ammonia, when the inverted species is identical to the original species, so there are not two distinguishable isomers. But in this case, the inversion produces an isomer that is chemically different, and one can then study the kinetics of that isomerization. Now, it was in that original RRKM theory, it was assumed that there's a very rapid equilibration of the vibrational modes in a molecule. That occurs within just a few vibration times. But Simon found this very large class of chemical reactions in which there were these significant deviations, and where in fact the rate determining step, in this case the rate determining step for the inversion at that nitrogen center, was really the distribution of the intramolecular vibrational energy among the various vibrational modes. And so this is just one example of a very large class of chemical reactions that Simon studied in that way. This was by gas phase NMR. That was a technique, an especially demanding technique, but Simon made it work in a very effective way. So this is the single pulse shock tube that Simon referred to. This is a paper that he did in collaboration with Ed Ressler, with whom he did a lot of collaboration in shock tube studies. I'm pointing out this one and this in particular. I'm going to talk about just one of the studies that he did with this shock tube, and this was the study of the decomposition of metal compounds in the shock wave. So the shock wave passes through a gas phase version of the compound, and there's a sudden change, a sudden increase in the temperature, local increase in the temperature that decomposes the molecule. And here in particular, one of the molecules that is studied in this paper is that of the vapor of iron pentacarbonyl. So now the shock wave passes through this iron pentacarbonyl. It decomposes it, the carbon monoxide comes off, and it leaves metallic iron in the gas phase, a high concentration of gaseous metallic iron at a temperature far below anything that you would think of as the vaporization temperature of iron. And so then immediately, so now one has a highly unstable gaseous distribution of iron atoms, which now immediately nucleate the formation of the condensed phase. And they were able then to study the nucleation of that vapor. Study the nucleation of the condensed phase from the iron vapor. It was a magnificent achievement, and just one of many of the chemical reactions that Simon and his collaborators studied with the shock tube. But then, of course, once you have this data on the nucleation of the condensed phases of iron, you need to compare it with what the theorists had to say about it. And what was found almost immediately is that the classical nucleation theory was not capable of explaining these experimental results. But he and our colleague, Charlie Wilcox, and together also with Steve Russo, then worked out a theory for the nucleation, and were able to explain with their theory, showing significant deviations from the classical nucleation theory, were able to show excellent agreement with the experimental measurements. Now, shortly after Simon left Cornell, so that was about several years ago now. Simon was no longer doing experiments in California, but that's not to say that he had stopped thinking about science. As you saw, he has a passionate interest in the history of science and in studying the development of various of the threads in science. And so not too long after Simon arrived in California, I got from him two essays that he wrote. Both of them on historical subjects. So you understand that now we're talking about Simon at the youthful age of 98 when he produced these essays. Here was one of them. This was a page from the history of science, English scientists and inventors of the 19th century. What it was, of course he went back, needless to say, to early historical times, but then the main themes in this essay were the relation between Humphrey Davy and Michael Faraday. And he talked about this relation between those two scientists. Michael Faraday was started as a young assistant to Humphrey Davy. And Simon went on to talk about how, in spite of their disparate social status, Humphrey Davy was a lord, and Michael Faraday had come from a relatively poor background. So Simon spent part of his essay on the sociology of the relation between Davy and Faraday. He then, of course, needed to make comments on the physical sciences in general in the 1800s and the implications for what was happening in science in the 1800s on its impact on the Industrial Revolution. I hunted in the archives and discovered an amazing triptych showing these three great scientists. That's Humphrey Davy is on the left. This is Michael Faraday, and this guy in the middle was their teacher. And so that was the first of the two essays that I got from Simon on that occasion. The second one had to do with Simon's studies of the history of ideas about extraterrestrial intelligence and extraterrestrial chemistry. In fact, so needless to say, he went back to the Greek philosophers. He doesn't do these things without their historical background. Went back to the Greek philosophers, talked about various theories about the model of the Earth and its place in the universe. In the time of the Enlightenment and the change in one's views about the sun being the center of the solar system, the Earth being the center of the solar system, the sun-centric model, and so on. And in addition to what was found in the present-day studies of chemistry occurring in the interstellar medium. So Simon, in his essay, talked about the Miller-Urey experiment. The Miller-Urey experiment, they took a sample of mixed gases that they thought were representative of the early Earth's atmosphere, and then sent an electrical discharge through that and analyzed the result. And the resulting mixture showed molecules that were recognized to be important building blocks in biological structures, amino acids, and so on. And Simon also, with his single pulse shock tube, did the analog of that experiment. So he sent it again, created a mixture of gases representative of what is supposedly the early Earth's atmosphere, sent a shock wave this time, not an electrical discharge through it, and was able again analyzing the results to find these species that were important in later biological evolution. There was at that time also a person in our astronomy department who was very much interested in this search for extraterrestrial intelligence. That's this SETI, and this search for extraterrestrial intelligence. And so Simon became interested. This was the beginning of Simon's interest in this entire story, and it was the motivation for it. Likewise, going back to the earlier of the two essays that Simon sent, he also made a Cornell connection in that case because studies of that period, the period of Davy and Faraday, and even earlier of Lavoisier and so on, were important in our Cornell department of the history of science. In particular, he referred to Henry Gerlach and to Pierce Williams, who were two very well-known historians. So now. Now, of course, Simon has not stopped writing these essays. In fact, he told me yesterday that he has a few more that I can expect to be receiving in the mail shortly, and I'm looking forward to that. Well, that was part one, and we're all looking forward to part two, and I'm sure that everybody here joins me in wishing Simon great success with that next chapter of his career in science, and very many more happy birthdays. Am I supposed to take questions? If anybody has a question, Sai will answer.
All right. So the next event in this celebration celebration is we will go out to the atrium and mix and drink and have good conversation before dinner. So thank you all for coming, and let's go converse.
So we're going to pause for a moment between our dinner and our dessert for some comments. I am Barbara Baird. I am the chair of chemistry and chemical biology, for those of you who don't know or can't quite believe it. Some things have changed since Simon first came to Cornell. And I am delighted to welcome you to this wonderful celebration of Simon Bauer's 100th birthday. I'm delighted to welcome you to Ithaca, to the Department of Chemistry and Chemical Biology, and this beautiful space in our new Physical Sciences building that we share with the Department of Physics and Applied and Engineering Physics. And we're just delighted to have this space that we can have occasions like this, as well as do terrific research and teaching, as we do in chemistry. So it's just really wonderful that we can gather together Simon's former group members, students, and postdocs who were so happy to come back and celebrate. And we're just delighted that Simon, of course, and his family came for this celebration that we've been thinking about for a long time. And a lot of thanks are in order. First to our birthday boy for turning 100 and going strong, and for Joe Chang for suggesting that it might be a good idea to celebrate this occasion, and for the effort he's put in to lead this, and certainly for Simon's family for helping to coordinate this, and for bringing and accompanying Simon here, both for bringing him here and also bringing yourselves. And a special thanks to Joyce Boda, who put so much thought and effort and love into bringing this together. Every detail was thought about and thought about and thought about, and with the help of Martine, brought this together. And it was a terrific amount of work, but Joyce and Martine really enjoyed it too, because of all the people that were involved and were coming. So I would really want to thank all of those folks, especially Joyce. So I have to say that, in fact, this is my mother's 93rd birthday, and I am especially appreciate the contributions of a very long and spirited life, and all that comes from that, and all the people that benefit from that. And that certainly is true of Cy Bauer, and so many people have benefited from all he has done over the years. That is also true of Harold Scheraga, who is going to talk to us a little bit about Simon's life and his contributions. And as you know, we celebrated Harold's 90th birthday not too long ago, and in fact his whole family is gathered this weekend to celebrate his real 90th birthday, and that is Miriam's. And rather than spending this little time with his family, he thought it was really important and wanted to come to this celebration for Simon and to be able to say some things about Simon and his life and his contributions. So I'm very happy to introduce Harold Scheraga.
Well, I want to reiterate Barbara's welcome to all of you for this celebration of Simon's century. How do we contemplate what a century is? Simon was born in the same year that Sun Yat-sen led the revolution in Wuhan, China, that overthrew the dynasty of emperors. And we all know what kind of century this has been and what has happened to China and to the US, to the world, and all of us. Now, in most of this century, Simon can be characterized as a key and loyal member of our department in many ways. His science, that Ben described so well earlier this afternoon, his devotion to both scientific research and teaching, his concern about the department, the university, and the world about him, and his friendship with us, his colleagues. All the rest is commentary about Simon, which I'll allude to, based on the 2/3 of the century that I have known him. I first heard about Simon Bauer when I was a graduate student at Duke in the early 40s. I'm referring to his work with Badger, which Ben referred to also, and in detecting hydrogen bonds by infrared spectroscopy, and then his subsequent electron diffraction work. While I was later a postdoc at Harvard Medical School, I shared an office with another postdoc, Chris Spork, who had been a graduate student of Kirkwood's at Cornell. So I learned a lot about Cornell from Chris Spork, and he told me that the best physical chemists at Cornell were Debye, Kirkwood, and Bauer. On my interview trip to Cornell in 1947, I was pleased to meet Cy. Not only the usual way in which you go through the interview trips, but Cy was also seminar chairman, and he took care of introducing me for my lecture. And right after my lecture, Debye wanted to settle the issue of whether they're going to offer me a job. So Cy told me to wait in the chemistry library. Well, Debye called a faculty meeting to make the decision as to whether they're going to offer me a job. Now, all you young faculty members don't even know where the old chemistry library was. What's going on here?
Great-granddaughter is upstairs.
Oh. You know where the west entrance to Baker is, and that's where room 132 starts. Well, from there all the way down through my office and my research labs and Garner Chan's research labs, right to the end, that was the chemistry library. And when Clark Hall was built, they decided to consolidate the chemistry library with the physics library in Clark Hall. Now, the thing about the chemistry library was that every one of us, faculty, students, all had keys to the library, so you could go in any time, day and night, when you wanted to go. And so I asked for the keys. I was chairman at the time. And I said, well, we want keys to the new library, but the librarians refused to give it to us. So I argued with them, and we arranged a treaty that instead of giving us keys, they would keep the library open 365 days a year from 8 a.m. to midnight. Well, that lasted not very long, although I even had the words in perpetuity and that didn't last too long, because after a while Christmas disappeared, Thanksgiving disappeared, and so on, and then the 12 o'clock became 9 p.m. and so on. And ultimately the whole idea eroded. My wife's a librarian, and when she came to interview, one of the first questions they asked her was, "Are you related to that fellow Scheraga?" Well, anyway, I was waiting in the library for the faculty to make a decision. After a while, Cy came down to tell me to go see Dubai, and Dubai said, "We're going to offer you a job as an instructor." I won't mention the salary. And at that time, young faculty served 3 years as an instructor before being promoted to assistant professorship. That is inflated now in recent times. Anyway, during those years, it was very easy to get to know Cy. He was always accessible, both as a friend and a colleague. So I wanted to discuss science with him, national politics, and many other things. Cy was always receptive, and you could really have nice discussions with him. Now, you also heard some reference today in Ben's talk, or in Cy's also, that he was a master at designing equipment for his research in electron diffraction, and later his monstrous shock tube equipment. Actually, our department, you heard about Harry Bush, and was an excellent machinist, and it was a very well-equipped machine shop. And so they did very well in building the machines, of course, which Cy himself was designing. In those days, you've already heard this one, Cy made one foray into theory. And that was, of course, the theoretical work with Ben Widom. And when Ben joined the faculty after he had a postdoc with Oscar Rice at Chapel Hill, just like Cy, Ben became a very good friend, accessible to discuss science and many other things. One of the things I liked about Cy was that he was never reluctant to take on a strong stand in the things in which he believed. He frequently wrote letters to the Ithaca Journal, attacking what was in the editorial columns, attacking what was in the letters to the editor with which he disagreed, and he was a frequent contributor to the Ithaca Journal. I remember also his performance at a faculty meeting. And those meetings used to be held in Boardman Hall. Now, Boardman Hall doesn't exist anymore. It was a really old building. Its location was where Olin Library now stands. It was demolished in order to build Olin Library. Well, anyway, that's where the faculty was meeting. As a matter of fact, when they were demolishing Boardman Hall, a large crane-like machine was driving down the road between Boardman Hall and Day Hall, and he couldn't find Boardman Hall, and so he asked an undergraduate standing on the side, which one is Boardman? And of course the undergraduate pointed to Day Hall. At one of those meetings, President Millot made a strong plea to the faculty to back a proposal of his. Of course, it was in order to bring in money, to send professors to nearby industrial institutes. And for those people in those institutes who attended those lectures, he was going to give them Cornell degrees. Well, the faculty overwhelmingly turned down that proposal. And Millot was very incensed. He embarked on a diatribe. He attacked the faculty for being receptive to new ideas, not being clever enough to recognize what he called a good proposal. Well, the whole faculty just sat there stunned. It was quiet. But Cy couldn't take this anymore. He leaped to his feet and told the president, "Mr. Millot, you don't understand what a university is all about." And he proceeded to explain why. When Cy sat down, the faculty applauded loudly. I said Boardman Hall was an old building, so they stamped their feet on those boards, and boy, they resounded very loudly. Millot just didn't say a word. He just adjourned the meeting. And he realized his proposal, of course, was dead on arrival. Just as an aside, I happened to talk about Cy when both he and Bill Miller retired. And Jack Johnson, who was a friend of Malott, invited Malott to attend the retirement banquet. I happened to be standing near the elevator in Clark Hall. It was in the top floor of Clark Hall where we have the seminars. And when Johnson and Malott emerged, I heard Johnson whisper, Malott whispered to Johnson, "Which one is the Bauer?" He obviously never forgot Cy. Well, being not only a great scientist, outstanding scientist, Cy was also a great teacher. He was tough on students because he expected very much of them. In fact, the students used to refer to his lectures as the hour with Bauer. But he took teaching very seriously. Early in his teaching career, he and Frank Long were assigned to teach the course in qualitative analysis. Together, they both revised the curriculum and wrote a series of lecture notes for students that introduced physical ideas such as equilibrium and thermodynamics, which made the qual course much more than merely a technique in analysis. Sometime later, the course was turned over to Mike Sienko and me, and we made very good use of the lecture notes that Cy and Frank Long had written. In fact, when Mike wrote his famous freshman textbook with Bob Plain, he incorporated much of what Cy and Frank had written in that qual course set of lectures. Mike made a lot of money, of course, from that famous textbook, and as a result, he and Carol were able to build a house on McGraw Hill. More recently, Simon undertook a very active role mentoring students. Just recently, in 2003, he wrote a pamphlet for teaching assistants, instructing them on how to handle fundamental concepts involving bulk properties and related atomic and molecular structure. In it, he posed several questions to illustrate the kinds of queries they could expect to encounter from the undergraduate students to whom they were expected to provide instruction. One can't talk about Cy without talking about Mitzi. They were both very good friends with Miriam and me, and we and our department colleagues all enjoyed much social interaction with them. Mitzi had a terrific sense of humor and always made people around her feel very happy. Miriam and I spent a sabbatic leave with Cy and Mitzi at the Weizmann Institute. Our children were with us. Ross Bauer was with them in Israel. And among other things, we had a wonderful trip together from Rehoboth through the Negev desert. We made many trips around, but that was one outstanding one at the southern tip of Israel. Actually, for a while, Mitzi taught Sunday school here in Ithaca at the temple downtown, and our kids used to attend her classes. Like Frank and Marion Long, Cy and Mitzi made the decision to settle in California to be near their children. And of course, as a result, we were all deprived of our close contact with them. Simon will always be remembered as an important person who contributed to making our department an outstanding one. I happened to talk not only at his retirement party, but also at one of his birthdays. I don't remember whether it was his 80th or 90th. I can't recall. But Miriam and I just recently downsized our house to move to Kendall, and of course I lost all my notes, so I don't have any notes from what I said at that time. But I do remember one phrase. I used the Hebrew wish for a continued long life and healthy life, ad mea ve'esrim, which translates in the biblical unto 120 years. Simon, may you continue in good health, a healthy life, doing the things you want to do, ad mea ve'esrim.
Thank you.